Okay, so towards the middle and end of organic, we're going to be drawing relatively complicated structures. And so while at the very beginning, maybe drawing this butane molecule as shown with all of the hydrogens and all of the carbons kind of drawn out explicitly, that might not be a big deal at the very beginning, but towards the end, that's kind of a time waster. And so there's actually a faster way of getting this information across to your viewer. So instead of drawing all of these hydrogens out, and instead of drawing all of the carbons out, we can do two different things. The first thing is we could draw a condensed structure that might look a little bit like this. And that might be a little bit faster, but it's still kind of, whenever you go from this very formal, explicit Lewis structure to this condensed structure, you're losing a little bit of information regarding the connectivity. And so the faster way of doing this, where you can get all of the information across, is with these skeletal structures. And so the way that you would make a skeletal structure that could very accurately represent butane would be like so. And so this is just as accurate as this molecule up above. So this is butane, and this is butane. This is probably the fastest way you could draw butane while still retaining all of the information. There are a couple of things that you have to remember in order to draw these skeletal structures. The first thing to remember is that every single point along the way that doesn't have an explicit carbon, you kind of assume is a carbon. So this point is a carbon, and so is this, and so is this, and so is this. So you could see 1, 2, 3, 4 carbons drawn out completely. The next thing is that obviously the carbon atoms themselves aren't drawn, so every single one of these dots, I wouldn't really draw these dots in the skeletal structure, but you kind of have to assume that these are carbons. And along with that, what you do is you also have to understand what's called an implicit hydrogen. And these are hydrogens that are not necessarily shown, but they're still present. So the rule is for skeletal structures, if I drew this molecule with 1, 2, 3, 4 carbons, and let's say we're examining this carbon on the end, even though I'm not drawing all 3 of these hydrogens, you assume that they're there. So what you do for carbon is that you always try to make sure that it's tetravalent. So we have 4 different bonds, and these other 3 bonds that aren't really shown, we have to remember that these are hydrogens. And so here we have 1, 2 bonds. To make this carbon tetravalent, we have to draw in 2 other bonds, and that must mean that we have 2 implicit hydrogens here, 2 implicit hydrogens here, and 2 implicit hydrogens there. So a lot of the times an issue is making sure you can very quickly see how many implicit hydrogens you have. The last thing that you have to keep in mind is that, let's say we were going to draw the following molecule right here. If we were to look at this yellow carbon right here, you would potentially be tempted to again put 2 hydrogens on this carbon. But if you did this, you wouldn't be making this yellow carbon tetravalent. You now have 1, 2, 3, 4, 5 bonds to this yellow carbon, which actually exceeds the octet rule, and so this is not a valid structure. So the way we would actually make this molecule valid is to simply draw 1 hydrogen right here. So now this yellow carbon is tetravalent. We have 1, 2, 3, 4 bonds, and so we have to remember that this has only 1 implicit hydrogen, not 2. And so this would have 2, 2, 1, and 3 implicit hydrogens. And then the last part is that for anything that's not a carbon, we actually do have to draw out all of the hydrogens. So for this oxygen right here, we couldn't get away with not drawing the hydrogen out. This would kind of be a little bit odd. You really wouldn't know what to make of this if you were an instructor or somebody who had been doing OChem for a while. So the rule is that for carbons, we don't have to draw hydrogens out explicitly. They're implicit only. That's totally fine. But if you have any kind of atom that is not a carbon, you have to draw out the hydrogens that are attached. So for this oxygen, if we didn't draw this hydrogen out, we would be making a mistake. And because the reason for that is that for these heteroatoms, so oxygen and nitrogen, we have to make sure that we give enough electrons to make sure that we fulfill the octet of these atoms. So this oxygen not only has 2 covalent bonds, it also has 2 lone pairs as well. So this oxygen has 2 lone pairs, and this oxygen also has 2 lone pairs. So that's a very quick and dirty explanation of skeletal structures and a couple of rules for those. The last thing to keep in mind whenever you're drawing skeletal structures is that for carbon, since we have this implicit hydrogen idea, we have certain rules for whenever carbon becomes charged. So let's say that we have a carbon with a positive charge, so like so. If we have this carbon in the center, and let's just say it has a positive charge, what really is being said here is that this carbon has to have, in order to have this positive charge, we had to get rid of a hydrogen. So really the way we would draw this out explicitly is we would draw that center carbon, we would have one hydrogen right here, and we would have a positive charge. So what's really happening is this carbon, one of its hydrogens has been replaced by that positive. So if we actually did the formal charge calculation for the center carbon, we could say 4 minus 1, 2, 3 is positive 1. So that explains the positive charge. And that's another reason why we don't have this fourth hydrogen right here. In this case, that positive charge really wouldn't be a valid way of drawing it. It's simply by doing the formal charge calculation. So the other charge state that we could have would be if that carbon has a negative charge. So what if we had this negative right here? What would that actually look like? So the same is really happening here for the negative example as was happening for the positive example, is you could really think of that negative as taking the place of one of the hydrogens. So if we drew this molecule out explicitly, we could draw one hydrogen right here, and we would have a negative charge that would take the place of the other hydrogen. But that negative isn't just there without any reason. We have to have some reason to have a negative. So if we did the formal charge on this carbon in the center right now, the way we have it drawn, we would have 4 minus 1, 2, 3. So it still looks like it's positive like it was for this other example. So the way that we make this negative is not only giving it a negative charge, but recognizing that in order to have that negative charge, we really have to put a lone pair on this carbon in the center. So now if we did the formal charge calculation, we could say 4 minus 1, 2, 3 bonds that are formal covalent bonds, and then we would subtract 2 more for each of the electrons for the lone pair, and that's going to equal negative 1. So this would be the scenarios that you might have to deal with a positively charged carbon and a negatively charged carbon.